Hi, I am Sathya, Assistant Professor, Department of Computer Applications, Keshav College of Arts and Science for Women, Tiruchendur. Now we are going to discuss about data structure and algorithms. Introduction to DSA. Data structure and algorithms are fundamentals in computer science that help us to organize and process data efficiently. They are used in solving common software challenges from managing large data setups to optimize the speed of tasks. DSA helps in sorting and managing data efficiently, making it easier to retrieve and use when needed. Whether it is finding the shortest path in GPS system or optimize search results in a search engine, DSA play an important role to solve such problems. By understanding DSA, you can design system more efficient, which is very important in areas like web application, database, and machine learning, etc. Abstract data types, the list ADT. Abstract data types separate interface from implementation. They define operations without specifying how they work internally. Lists are ordered collections with dynamic size. They form a fundamentals building block in computer science from managing collections of efficiency. List ADT core operations: insertion, add element at a specified position, deletion, remove elements at specified position, traversal, visit each item in sequential order, merge, combine two lists into single list. Array based list implementation advantages: fast random access, simple index, memory locality. Limitation: fixed size, costly insertion, inefficient deletions. Introduction to linked list. Node-based structures. Each element contains data and pointers to other nodes. Dynamic size grows and shrinks to needed without costly resizing operations. Efficiently modifications enables insertion and deletion when position is known. Singly linked list structure. Each node contains data and single pointer to next node. Traversal: one directional movement from head to tail only. Indicator: lost node to null, marking to end of the list. Circular linked list: node A, node B, node C. Starting point can be any node. Node B, middle elements like regular list. Node C, last node pointing back to first. Double linked list: previous node, current node, next node. Previous node contains backward pointer to previous element. Current node contains data and bidirectional links. Next node contains forward pointer to next elements. List operations: insertion, deletion, merge, travels. Operations: array list, linked list. Applications: polynomial manipulation, addition, merge two polynomial list, term management, insertion, deletion, modification term, storage, co-efficiently export in each node. List ADT in practice: implementation choice, performance considerations, applications. Stack ADT and queue ADT operations and applications. Welcome to our exploring the stack and queue abstract data types. We will explain their core operations and practical applications in computing systems. These fundamentals such as power everything from expression, evolution, process, scheduling in modern computing environment. Understanding stack ADT. What is ADT? Abstract data types define both data and the operations that can be performed. They provide a blueprint without specifying implementation details. Stack principle: stack follow the last in first out principle. Think of the stack of plates you can only take from the top. Implementation options: stack can be implemented using array or linked list. Each approach offers different performance trade-offs. Core stack operations: push, insert a new item at the top of the stack. Pop, remove and return the topmost item from the stack. Pick, view the top item without removing it. Is empty. Check if the stack has no elements or it at the capacity. Applications of stack: undo, editor, store previous status in a stack of queue reversals. Syntax parsing: compiler use stack to validate nesting programming structures. Web browsing history: backward navigation leverages stack principles. Call stack: function execution tracking in program memory management. Evaluation: arithmetic expressions using stack. Parse expression: scan the expression from the left to right. Identification operations and operands. Process elements: push operands onto stack. When encouraging operations, pop required operands. Compute results: apply operands to popped operands. Push result back to stack. Infix postfix conversion with stack. Read infix process expressions like a plus b into c character by character. Apply algorithm, use stack to manage operations based on preceding rules. Generate postfix output becomes a b c int plus ready for the efficiency evaluations. Understanding QADT. NQ, DQ, status check, peak. NQ, add element at the rear of the queue. DQ, remove element from the front of the queue. Status check, verify if queue is empty or full. Peak, view the front element without removing it. Circular queue and priority queue. Circular queue, front and rear point wrap around array boundaries. Eliminations need to shift element after DQ operations. Maximize storage of efficient in fixed size implementation. Priority queue element has associate printers determining DQ order. Higher priority element exit before lower priority ones. Often implementation using heaps for optional performances. Applications of Q and DQ. Processing schedule. Operating system manage CPU time using queue structures. Prints boolean. Document printing requirements wait for first in first out queries. Requesting buffer. Network packets await processing in queue buffer. Graph algorithm. BFS traversal delay on queue structures for level ordering. Summary and key takeaway. Core data structures, essential operations, real world applications. Thank you.